Hello and welcome to the class on the expanding universe today. So I'm Laura Lewis and let's get on to the learning objectives. Got a bit of animation there for the next slide. Okay, number 1, describe the steady state and the Big Bang Theory using evidence. So there's only evidence for one of those, we'll find out. Understand that the universe is expanding at an accelerating rate and that galaxies are moving away from each other, detected by redshift. And number 3, how to answer questions on the expanding universe. So number 1, so we're going to look at an old theory in cosmology. So the study of the universe is called cosmology. It's a steady state theory, okay? So this theory states that the universe has always existed and it will continue to exist. So it does sort of seem like that, doesn't it? So when you look in the sky at night, you probably wouldn't suspect it was moving or anything. Planets move at detectable speeds, obviously the moon and sun, but stars don't really seem to move too much. So it's understandable why people thought this. But the theory also states that the universe is static and not moving, and time has no beginning or end. So that was a key point here about steady state. There's no definite beginning of the universe in this theory. So there's no hard evidence for this other than that the universe exists. So that was a key point of steady state, is there's not really hard evidence of it. It's obviously just how it seems to appear, doesn't it? So people honestly did think this was true for a very long time, until the 1920s and things actually. So it's not an archaic theory. You can kind of see why. So the theory that you probably know about today is the Big Bang Theory. Okay, it actually began as a joke. Okay, that's why it's got a bit of a funny name, because it began as a joke. So it was an astronomer called Fred Hoyle who actually didn't believe in the Big Bang Theory at the time. He said, "Oh, the other theorists and their Big Bang Theory is a bit of a joke," and it kind of stuck. The name stuck to it. So the Big Bang Theory states the universe had a beginning and is expanding. So that's the main point of that, is that there's a beginning. And there is evidence for the Big Bang Theory. Okay, it's a cosmic microwave background radiation. So radiation picked up on dishes like this. We can detect there's a radiation all over the sky. Okay, we can't see it with our eyes, we can see it with a big radar dish like that. And it's obviously evidence for something happening, okay, a long time ago. And it's all over the sky. And also redshift. So what we're going to talk about a lot today is about redshift, okay? Okay, so in the context of redshift, we're going to first of all talk about the Doppler effect. Okay, it's quite similar to redshift. So you can think of it being similar. This is another part of science anyway, the Doppler effect. So, example, if you have a vehicle that makes a lot of noise, like an ambulance, like here, as it moves towards you, it sounds like it gets higher pitched, and as it moves away, it sounds like it gets lower pitched. Of course, it wasn't moving at all; it would sound the same all the time. There is a reason for this. Okay, so the wavelengths of the sound get squashed, they get shorter and smaller, you see here, as it approaches you. As it goes away, it gets stretched out. So the wavelength gets longer if the ambulance or other sort of emergency vehicle is moving away from you. But anything making a siren noise, you'd hear that. Okay, a loud siren noise, you'd hear it. So the waves would bunch up as they approached you. It's a good diagram. And they would space out or spread out if it's moving away from you. Okay, that's the context. That's the Doppler effect, but we're going to talk about redshift today, which is similar. Okay, so again, for a little bit of context, if we go on to redshift, is that all elements have a spectra. Okay, so if you pass the light from different elements, say, for example, you're burning hydrogen and it makes a light, say you pass it through a prism, it would appear, a rainbow would appear, or a spectrum would appear, and dark lines would appear on it. Okay, and these dark lines are in different places different elements. So it's like its signature. It's got its own sort of pattern or signature, or like a barcode, really, in a way. Look at that barcode. Hydrogen. So hydrogen, helium, you can see here. There are some lines that some of them share, but overall they are different. So that's a famous double lines of sodium there. Okay. And we can do this with stars and galaxies. We can pass their light through prisms. I've actually got one of my telescopes, and they're quite easy to obtain. You can just buy them. Okay, and to do this with stars and galaxies. So it's not actually that specialized piece of equipment. Anyone can do it. Okay, so you pass the light from a star through a prism, okay, or a lens with a prism in it, and you get a spectrum. Okay, and you can tell what that star is made of, what elements it's made of, according to its spectrum. You can do it with the sun as well, but obviously not point a telescope at the sun. Best to do with stars. It's a lot safer. Okay, because you probably need specialist equipment for the sun, but with stars at night, you can do it with the telescope. Okay, so you can see they're all different lines. So they've all got their signatures. This is like in it's called a laboratory frame. So sometimes on a test, you won't see it as a rainbow background. So it looks a bit more confusing, but I'm going to show you because lots of students I've taught got this bit mixed up. When they saw it as a rainbow, it was a bit more obvious to them. But sometimes text papers, they don't get printed in colour, do they? So sometimes they'll show it to you in black and white. So the wavelength is the key here. So wavelength of 400 to 700. And helpfully at the top, that says that's the red end and that's the violet end. So it's like that, but just in black and white. Okay, so I've shown you two. I'm just saying test papers will come in black and white. So making sure people get used to that. So what we can do is look for a certain element. Okay, so example, this is, and it's called a laboratory reference. So say example, let's have a look at an element. It's got a bold line. Say it was iron there. Okay, it's got a big bold line. So say example, that's iron's spectrum. They burnt some iron, heats up to a very high temperature, and it emits light. So we can do that in the laboratory. It's called spectral analysis. It's got a big bold line there. So in laboratory reference, that means literally in a laboratory. Okay, we can look at that. So lots of stars got iron in them. So we look at a nearby star. Let's move that way a little bit. So that bold line, that big line, is moved that way. It's moved towards the red end of the spectrum. Okay, so it's a little bit red shifted. We call that red shift. It's very straightforward, really. Red shifted. So some stars will be blue shifted. They'll be moving this way. I'll talk about a question about that later because I catch people out on that. Because sometimes stars are blue shifted. There's a difference between stars and galaxies. Some nearby stars might be moving towards us a little bit. A nearby galaxy, a little bit red shifted as well, a bit more than the star. That's moving away from us. The wavelength has got longer, so that way it's getting longer. It's moving away from us, so it's red shifted. There is one galaxy that is moving towards us, so the Andromeda Galaxy. It's in the sky, and that will be blue shifted. So again, always look carefully at these diagrams, especially for nearby ones, because obviously they gravitationally interact with our galaxy, okay, and they could be moving towards us or not at all. But it's always the same rule when we get to the more distant galaxies and not gravitationally interacting with our own. So they are very redshifted. So it's very noticeable when we get to the distant galaxies. So they're very redshifted, and a very distant galaxy hugely redshifted. So it's moved the further the galaxy is away from us, the more it is redshifted. Okay, so that's found out in lots of galaxies, lots of studies have been done. So the further the galaxy is away from us, the more it is redshifted. So what does that mean? Let's get onto a graph. Okay, so Hubble, looked at these galaxies. Okay, quite a long time ago, over 100 years ago now, about 100 actually, exactly. So he looked at that. So that's a modern image today. So he didn't see that image. That's a modern from the Hubble Space Telescope, which is named after him. So he got it named after him because his work was so important. Okay, but he managed to plot, as I said, you can actually use a normal telescope and a prism to do this work. So he did it. Okay, so he plotted the distance of the galaxy. You can use this using certain types of star and their brightness. You don't have to worry about that today, but you can use a different distance measurement to do that. And it's called their recessional velocity. So that means how fast they're moving away from us. Okay, and that was by the redshift. So it's quite a linear relationship. There's some measurements. Remember, this is the original data he got. There's been more refined data, but you might see this in the exam. His original data, I've worked with it. Okay, it does show though, the further the galaxy, the faster its motion away from us. And there is a relationship, V, velocity of the galaxy, equals h naught. H naught is called the Hubble constant, again named after Hubble. So he actually invented it. D is the distance from the Earth. So you'll see that V equals h naught d. Okay, so what we're going to do is do some questions to check. So in 1929, I was thinking that it's nearly exactly, isn't it, 100 years. In 1929, astronomer Edwin Hubble observed the light from galaxies moving away from the Earth had longer wavelengths than expected. What name is given to this effect? So it's only 1 mark, and that's redshift. Okay, so I'll get to the longer answer, make you think for a bit in a minute, but let's just do some simple first of all. So again, exactly, you will see his data in exams. So from his observations, these are taken from exam papers. So from his observations, Hubble was able to calculate the speed of a galaxy and the distance of the galaxy from the Earth. So figure 1 shows the results of Hubble's calculations. So again, we've got distance in kilometers, and they're very long distances, don't worry too much about that. Speed of galaxy away from the Earth. What relationship between the speed of the galaxy and the distance is suggested by Hubble's results? So I'll let people pause and think about that one for a moment. That's be given 2 marks to be given, but again, it's very straightforward, that one. So it was actually written on the slide before. Okay, so this is how I'd write it out. The further away the galaxy, the faster the speed of the galaxy. So it's a linear relationship. Okay, it's a linear relationship. Okay, so a little bit more involved. Yeah, so yeah, that evidence of the expanding universe was only discovered, 1929, and it wasn't actually taken that seriously first of all. It took a long time for it to sort of permeate, so get into scientific communities. They didn't accept it first of all. It was quite a shock to a lot of people. Okay, so it wasn't actually that celebrated at the time, but later on it was more accepted. So in the 1950s, there were 2 main theories to explain how the universe began. So theory 1, so yeah, some steady state theories will say the universe is expanding slowly, but it still didn't have a starting point. Now, so theory 1, the universe has always existed. It is continually expanding. So that's one type of steady state theory. There were some types like that. So new galaxies are formed as older galaxies die out. Okay, that's a theory, remember? Theory 2, the universe began from a very small region, sort of a place, that was extremely hot and dense. The universe has been expanding ever since. They probably obviously recognize that one. In what way did the observations made by Hubble support both theories 1 and 2? So it's quite subtle that those 2 theories that they've given you, remember, the ones they've given you need to talk about, not other ones, those ones they've given you. Why does it support it? So have a think for a minute. Okay. Hubble's observations of redshift support an expanding universe. So you can elaborate on that and say both theory 1 and 2 state an expanding universe, but that would get you the marks. Okay, so a little bit more on that. Isn't only 1 mark there. Most scientists now believe theory 2 is correct. So remember that was the one about the small dense region expanding. Big Bang theory, really, isn't it? So suggest what is likely to have caused scientists to think theory 1 is wrong. So there's think about this, what I said before, there isn't really any evidence of these things. So I would write, there is no evidence of galaxies being created or destroyed at this moment in time. So yeah, we don't observe it, so we don't have that evidence. Okay, this one looks more complicated than it really is. So scientists can use the visible light spectrum from distant stars to determine whether the stars are moving. So the visible light spectrum from stars includes dark lines at specific wavelengths. So the lines we saw before, like a barcode. The diagram shows the visible light spectrum from the sun and 4 other stars. Okay, so they're stars. A, B, C, and D. There's the sun, and could be the double lines of sodium. So you might use actually a lot. How does the speed of star B compare with the speed of star D? So B is more redshifted than D. Okay, so let's have a think about that. So speed of star B compared with the speed of star C. So let's have a think. So speed. So we've got the sun. Okay, and that is so B compared to the sun, and D. Remember that even though that one looks like it's, they're actually both blue shifted compared to the sun. Again, this is one to catch people out. This one, okay, and it's blue shift. I said this with stars, they might do a blue shift on you, okay, and not a red shift. Okay, that's why I've included these. So D compared to B is actually more blue shifted compared to the sun. So speed of star B is less than the speed of star D. Okay, so D is moving towards us faster. Okay, a universe one. So the Big Bang Theory is one theory explaining the origin of the universe. The graphs X, Y, and Z show how the size of the universe may have changed over time. Okay, so have got that one. Size of the universe is the same, it looks like. Size of the universe, start of time, size of the universe. So which graph would the Big Bang Theory suggest is correct? Explain your answer. So have a think about that one. Right, so Y, the second graph, okay? So Y, so as the universe started from a tiny point, so yeah, so Y, an explanation is as the universe started from a tiny point and has been expanding ever since. So looking at that, the second graph along there, Y has got origin. The other one next to it doesn't start at 0. Okay, so that's not the Big Bang Theory. It could be a different theory, but not the Big Bang Theory. Okay, so always be careful about that. So thank you for listening today. Okay, I hope you enjoyed the video, and I hope to see you in a different video. Thank you. Goodbye.